Mute. Okay. Hello, and welcome everyone to the Ask Seminar series. This is the first of our in-person seminars this fall, and I think we have 3 more in-person seminars coming up, and of course, a number of virtual ones. Please feel free to ask any questions after the presentation, and you can do so by grabbing a mic from me. And also, since this is the first one, we are happy that our Associate Director, Ralph, is here, and our lead Ralph to introduce the speaker before he gets started.
Yeah, thanks, John, for putting this together. I just want to welcome Justin Pflug, right? Let's pronounce it the right way. Who's an assistant research scientist here at ESSEC, been here going to your 3rd year. And he's going to tell us about some of the work he's doing with NASA, with Sujay Kumar, about snow remote sensing and modeling. And you got your degree in civil and environmental engineering in University of Washington. All right, so welcome here and look forward to your talk.
All right, great. Thank you, Ralph. Thank you, John, and thanks everyone for having me. It's really awesome to be here with you today. Like Ralph said, I'll be talking really high level about some projects we've been looking at, how to use information that we have at our disposal from remote sensing to better constrain our estimates of snow in this variety of snow climates. So before diving in though, I am here with you on campus today, so I think it is important to include a land acknowledgement. This is from University of Maryland's Office of Diversity and Inclusion. Truth and acknowledgement are critical in building mutual respect and connections across all barriers of heritage and difference. So we acknowledge the truth that is often buried. We are on the ancestral lands of the Piscataway people. We're the ancestral stewards of this sacred land. It is their historical responsibility to advocate for the four-legged, the winged, those that crawl, and those that swim. They remind us that clean air and pristine waterways are essential to all life. This land acknowledgement is a vocal reminder for each of us as two-leggeds to ensure our physical environment is in better condition than what we inherited for the health and prosperity of future generations. And before diving in, I also do want to provide huge thanks and acknowledgement to a lot of the study co-authors on the work that I'll be presenting today, and also the sources of support and funding. All right, so for today, I kind of wanted to frame everything in this sort of 2-dimensional resolution space, right? And why I want to do this is because how we look at snow, how we care about snow and the snow's applications in the environment really does vary as we move in this 2-dimensional space. So for example, we know that, at these larger global and climate scales, how snow is a very, very important facet of our climate system on the Earth's land surface. Yet we also know that in future climates, the state of snow is pretty threatened in a lot of these regions. So for instance, here in the southwestern United States, there's a study from 2021 that's suggesting, for this historical snow-covered area, about 50% of that area is expected to see low to no snow conditions emerging by mid-century. And this is a really big deal, right? Because snow-fed water resources are very important for our local economy. They provide water for municipalities, for agriculture, and they sustain the environment that we care so much about. And there's a study in 2017 that suggested at these basin annual scales across the western United States, this 50% loss to snow that I referenced in the previous slide would equate in a loss of economy about $4.7 trillion, which is more than the government takes in from taxes all year round. And this is important to mention that this is only for the western United States, and that is in 2017 dollars. So we'd expect that to be larger now. And these even finer spatial and temporal scales, snow is an important driver for, disasters such as rain on snow flooding. This is a photo from some of the devastation that occurred in 2022 in the Yellowstone area. And at even finer spatial scales, how snow is distributed across the landscape is very important for local ecology. For instance, it provides denning habitat for polar bears, for wolverine, and it provides refugia for local wildflowers and nature. So, despite these applications that I've laid out, how we look at snow doesn't always nicely correspond with these applications. So, for instance, this is a photo of myself collecting field measurements in Alaska. And, while I'm collecting very interesting information and very awesome information about the snow characteristics and water content and things like that, it really is only specific for that point in time and space. And so what we want to ask is, can we actually use information from these points and combine them with other tools to actually estimate snow across these larger spatial and temporal resolutions? And one way that we commonly do this is by using land surface models. Yet we also have significant uncertainties in our models, right? At these climate scales, for instance, we have uncertainties about how we as humans will respond to the growing challenge of climate change. Perhaps our biggest source of uncertainty is that we have a lot of uncertainty in the actual meteorological data that we're giving to our models to force our snow simulations. And I'll be talking about this a lot today, because especially in these snow-covered regions like mountains and the Arctic climate, we don't really have a lot of ground-based observations to constrain our estimates of the meteorological conditions. And then we also have process-based uncertainties. So for instance, in this 2020 paper that I'm showing on the right, we see pretty massive differences in how snow is distributed across the landscape, provided different model representations of a process like wind redistribution. So to us as a community, this really means that we have to use all the data at our disposal, right? And then this includes remote sensing platforms to better constrain and hone our estimates. So what I'm showing with these red boxes here are platforms, to my knowledge, that have been used to look at snow in one way or another. But one thing I want to stress is none of these should really be considered a snow-focused satellite. Really, these observations up there for different purposes in most cases. And what that means for us as a community is that we've sort of been making do with these observations, trying to squeeze the most information out of it as we possibly can. And that's really going to be kind of the focus of today's presentation. And specifically, I'll be focusing today on observations of snow cover provided from the Landsat platform, MODIS, and also these novel commercial satellite imagery from PlanetScope, these PlanetScope Dove satellites. All right, so for today, we kind of wanted to hit this right out of the bat. Just look at this huge overarching question, right? How can satellite remote sensing inform and constrain our estimates of snow across a wide variety of both these spatial and temporal scales? And so I'll be kind of presenting in 4 major sections today, each of which kind of has this overarching issue or problem that we're detailing. In section 1, we know that precipitation volume and distribution is often very biased in mountainous locations. So our question here is, can we actually use observations at our disposal, such as snow cover patterns from remote sensing to bias correct these current year estimates of snowfall? In section 2, we also recognize that our most historically used snow cover observations from remote sensing aren't at very fine spatial scales. They can't actually look at the snow at drift scales, say 10-meter resolution or finer, that is really important for the local ecology. So here we wanted to see if we could turn to this new data that's coming out of the commercial sector to actually address this. In the third section, we kind of want to return to this thought that, our snow models themselves are limited by inaccuracies in both the forcing and the processes. So we wanted to see if we create a model that's more flexible, something that's set up to take the data that we trust most, such as our most trusted model forcings and our observations of remotely sensed snow cover. And in the last section, we want to return to this idea that no snow-focused satellite currently exists. But what if we had one? This is an important question to ask. If we had a snow-focused satellite, how well would we actually be able to estimate our global snow water resources? All right, so let's hop into this first section. This is covering some work that was published in a 2022 paper shown here in the bottom right. The basic premise here, like I said, is we have pretty massive uncertainties in our meteorological forcing, in particular snowfall in mountainous locations. So for this conceptual shown in the upper left, this more rugged surface represents the land surface at approximately 20-meter resolution over some mountainous location. And this more flat plane here actually represents the estimate of elevation from a coarser resolution meteorological data set. And over this region, we're really constrained to have one estimate of domain average snowfall from our meteorological data set. And this is an issue, right? Because in mountainous locations, as you change distances very, horizontal distances by very small amounts, we see pretty significant changes to the snow deposition across this landscape. And to us as snow scientists, this means we have to find a way to downscale. And one of the most popular ways to do this is by using these pretty simplistic statistical approaches. In this case, we say, snow deposition in every grid cell is mean snowfall multiplied by some precipitation factor based on the difference in elevation between these two products. Yet, this is really assuming that increases and decreases in snowfall really only correspond with increases and decreases in elevation. And we know that there's a whole host of reasons why that's really not the case. All right, so in this study, what we really want to do is figure out if we could find a product from the whole field of literature that's doing a better job at capturing these complex snow patterns in mountainous landscapes. And here we really turn to this product called the UCLA Historical Snow Reanalysis. You can kind of think of this as a land surface model, yet it's provided a whole range of meteorological forcings and a whole range of model parameters to actually simulate an ensemble of snow simulations. Shown by these gray lines up here in the top right. That's evolution of snow water equivalent, or SWE, measurement of water content contained in the snow for one grid cell. This product then takes observations of snow cover evolution as observed by satellites to retroactively reweight those simulations that perform better. And here what we found is, because it actually has this ability to adjust precipitation in space and time to more confidently estimate snow and based on how it sees snow cover deplete, it actually had the benefit of resolving snow deposition processes and complex terrain fairly well, and especially better than other data sets. One drawback, though, is it's not available in real time, right? It needs observations of how snow disappears to actually retroactively reconstruct the snow. And another drawback is it requires this large ensemble of simulations, which can be fairly computationally expensive. So here, building on some previous work, we found that in mountainous locations, oftentimes how snow is distributed is really a function of these overall prevailing meteorological patterns and their interaction with static terrain. And as a result, you tend to see these locations that have these snow accumulation patterns that have some level of interannual repeatability. Whereas, there's deep snow in one year, it'll be deep in year after year after year. And if you have that sort of information, this suggests that you should actually be able to adjust your snowfall input into your model as a substitution for more complex processes. We're talking things like wind redistribution or preferential deposition, avalanching, canopy effects, things of that nature. So if we have this trusted reanalysis, we should be able to go back in time and actually mine snow accumulation patterns from that. And one question here, though, is because this is not available in real time, how do we actually go back in time and find the most representative snow accumulation pattern in real time? All right, so in this study, we looked at a number of domains, but for today, I'm just going to be focusing on the Tuolumne River watershed. This is a location in the California Sierra Nevada. This is a very important location because it is a major source of water for the California Bay Area. And specifically, I'm going to be focusing on the upper extent here, the upper Tuolumne River watershed, the snow-dominated basin. And I could talk potentially the whole presentation about this, but we investigated a number of approaches for identifying this historically representative snow accumulation pattern. And we found overall the best way to do this was to use early spring snow cover as a matching criteria. So for instance, let's assume that we live in 2014. And this morning we got up and we have an observation at our disposal of snow cover from Landsat, as shown here on the bottom right. We found that we could actually use that map to actually go back in time and find a representative spring pattern from a different year, such as 1998. So using this reanalysis, we should be able to calculate a snow accumulation pattern from the reanalysis. And what's great is that we not only have these snow patterns, we have local observations of snow accumulation in our domain as well from these snow pillows. If you're unfamiliar with these are kind of just weights that measure the weight of the overlying snowpack and convert that into a measurement of snow water content or snow water equivalent. And here, if we have this pattern for reference, we should be able to relate snow accumulation at each of these snow pillows versus snowfall across the larger basin, both the total volume and the spatial distribution. So to kind of put this in another way, we're using snow cover as a searching criteria to find historically representative snow accumulation patterns, which we're then combining with our snow pillows to estimate basin scale, snowfall volume, and distribution. All right, so to show some results, what I'm showing in this plot are model estimates of snow depth over the upper Tuolumne River Basin on 7th of April in 2014. On the left is a simulation that used snowfall downscaled using this more statistical approach. On the right is our pattern-based approach, which combined our historical reanalysis with snow pillows. And we chose this date because we actually had the benefit of an airborne LiDAR observation of snow depth, as shown here on the further right. And visibly, we can see our pattern-based approach is doing significantly better. And if I have to convince you of that a little bit more, what I'm showing in this plot are estimates of snow water equivalent on the x-axis versus terrain elevation on the y. And we can see our pattern-based approach really only is estimating increases in SWE with elevation with very little heterogeneity across these different elevation bands. And this is opposed to our pattern-based approach, which is matching these observations really well, right? We see a significantly higher spatial variability and SWE that tends to increase to about 3,200 meters, beyond at which it actually decreases. So in this product, we were really excited to see kind of the applications that snow cover could have to link in real time these historical snow patterns and actually estimate snowfall significantly better than our statistical approaches. Yet, we also recognize that this approach and the resolution of our snow deposition estimates are really limited by the resolution of our snow cover observations and of our historical reanalysis. And both of those are coarser resolutions than, say, the fine scale distribution of snow that's important for local ecology. So to show an example of that, what I'm showing in this base map here is late spring snow distribution. This is in the Wyoming Wind River Range. And if I were to just kind of put some satellite footprints over this, we can see from MODIS that we're clearly not able to capture these individual snowdrifts. They're very important for things like wolverine denning. And even Landsat, while at a finer resolution, isn't at this 10 meters or less resolution that's really important for local scale ecology. So here we wanted to see, what sort of information could we get from the commercial sector, and specifically this constellation of small satellites provided by PlanetScope. They're called PlanetScope Dove satellites. And this is a slide I stole from an individual at Planet Labs, so I want to give credit here first and foremost. But at the time this slide was made, there was about 180 of these satellites viewing the ground at about 3-meter spatial resolution, viewing the Earth about 200 million square kilometers of the Earth per day. And since this slide was made, I believe the number of these satellites has ballooned to in the low 200s. And as a result, we're actually able to see the land surface at about 3-meter resolution at sub-daily time steps, here assuming that we don't have blocking by cloud cover, which is a bigger issue in some regions than others. I'm not going to go deep into this, but using this imagery, we actually classified snow cover at 3-meter spatial resolution. And we did this using an approach that was developed by Keihan Yang in 2023. Keihan found that you could actually use the red, green, blue, and near infrared retrievals with a machine learning, random forest machine learning classification model. So for instance, for these 3 domains shown here in the different rows, and the imagery that you see here on the left, we could actually classify snow cover at 3-meter resolution, as we see here on the right by these green shaded regions. And you can see relative to LiDAR observations that it does really, really, really well. So we did this for 7 different domains in Colorado and California over all the cloud-free observations that we had at our disposal from 2019 to 2023. What I'm showing here is a domain called Ostrander Lake in the California Sierra Nevada. And what I'm showing on the right is the date of snow disappearance expressed as the number of days from October 1st. And, we can see annual differences in the date the snow disappears. Yet if we were to actually normalize each of these maps by their domain average date of snow disappearance, we notice these patterns once again emerging year after year after year. These regions with earlier snow disappearance, as shown by these red pixels, are appearing in the same location, and the same could be said for these pixels with later snow persistence, as shown by these blue pixels. So here, provided this data, we wanted to ask, provided the finer resolution and higher frequency of this PlanetScope imagery, can we actually reconstruct drift scale? We're talking 3-meter resolution and daily spring SWE evolution using a simple reconstruction approach. And what I really want to emphasize here is the word simple, right? This is an enormous amount of data that we haven't had at our disposal before. So to us, this suggests that we should be able to actually inform things about the snowpack, such as wind drifts or avalanches, without the need for more complex models that tend to physically represent those processes. And maybe for the office fans in the room or online, we can think of this as maybe channeling our inner Kevin Malone and asking, why waste time do lot work when few work do trick, right? Let's stay simple. Let's try to do as well as we can given the data we had without making things overly complicated. All right, so to do this, we performed 3 modeling methods. Here in method 1 is the simplest approach we could physically think of. So here what we're doing is we're combining our 3-meter date of snow disappearance as observed by Planet with the snow melt that we observe from the nearest snow pillow. And if we have information about the rate at which snow is melting and the date at which it disappeared, we can actually look back in the spring and infer what snow must have looked like in order to have melted out on that date, right? This is overly simplistic, a number of reasons why this isn't necessarily the case, but it really hinges on these 2 key assumptions. The first being that snow melt rates in our meadow match the snow melt rates at the nearest snow pillow, which is not necessarily the case. It also assumes that the 3-meter rate of snowmelt across our domain is exactly the same for every single pixel, which again is not necessarily the case. So we wanted to add a method to this. Let's make it a little bit more complicated to address one of these assumptions. And to do this, we kind of leveraged this approach from this 2004 paper by Glenn Liston, where he assumed that snow distribution over any location, such as a mountain meadow, could be reasonably represented using a log normal distribution, such as you have at t equals a here. Then throughout snowmelt, you kind of picture us sliding this distribution off the left side of this plot, right? And as you move from time t equals a to t equals d, the percentage of your domain or your fraction of your domain covered by snow is the fraction of that distribution that lies right of the y-axis. And what's cool from PlanetScope is we don't only have observations of the date of snow disappearance, we have a time series of information about the fractional snow-covered area across our domain. And to us, this meant that we could set up a whole number of tests, a whole number of ensembles, as shown by these different gray lines, that use different initial SWE distributions and different rates of snowmelt to identify the snowmelt rate that best corresponds with our observed snow cover in this domain, in this case shown by this black dashed line. And in doing so, we are no longer assuming that our domain average snowmelt rate is identical to what was observed at the nearest snow pillow. We're actually allowing this to adjust. But as you may note, we're still assuming a spatially uniform snowmelt rate across our domain. So method 3, we just wanted to tackle that. We made it slightly more complicated. We just broke our domain into these different snow classes, as shown here by the different colors, and repeated method 2, allowed melt rates to adjust across each of those individual snow classes, as shown by this plot here. And of course, in doing so, we're allowing different number of snow melt rates across our domain, and we're also allowing those to vary from the nearest snow pillow. All right, just to show some quick results, what I'm showing here are estimates of 3-meter SWE distribution on 24th of May, 2023, using these 3 different approaches. This is for a domain called Devil's Postpile in the California Sierra Nevada. And we chose this domain because it actually had the benefit of having an airborne LiDAR-based estimate of snow water equivalent. So what I'm showing here in the second column is the same data as in the left column, just coarsened to 50-meter resolution to match the resolution of our LiDAR estimate shown here on the right. And visibly, we can see that we're doing amazing, right? This is a totally independent data set, and we're matching it almost perfectly. And this was the case not only in this domain, but we're seeing this across our 7 different domains across our 5 different years. And I'm not going to dig into the statistics too much, but overall, what we found is as we moved from method 1 to method 2, and we allowed our melt rates to vary, by adjusting our snow melt rate, we're capturing the SWE spatial variability across our domain significantly better. What was interesting to us, though, is as we allowed different portions of our domain to melt at different rates, we weren't necessarily doing better. To say here, as we go from method 2 to method 3, we were noticing overall very similar performance, suggesting to us, at least for our mountain meadows that we were looking at, we could represent snow melt fairly well, just assuming a spatially uniform snow melt rate. All right, before moving on, I kind of want to zoom us into a couple domains where I think some interesting things are happening. This is a domain called Dana Meadows in the California Sierra Nevada. This is also in the upper Tuolumne River watershed that I discussed earlier. And I think this photo that I found on the right is taken from somewhere near this white dot. I don't know if you can see my cursor. Nope. Oh yeah, kind of. And I think it's looking southwest over the domain. And what I want to draw your attention to is this red line that I've drawn over the hill in this meadow. And if we actually overlay our snow map, sorry, it's a little slow, we can see that our snow map is estimating larger amounts of snow on the north-facing side of the slope relative to the south. And by doing a bit of a dive on the literature, we can find that this has actually been observed by others, right? For this 2018 paper by William Currier, they found significantly larger amounts of snow on these north-facing slopes in this domain relative to the south-facing slopes. Looking here at another domain, this is Willow Creek Pass in Colorado. I believe this photo on the right is taken from the north part of this domain, looking south over this mountain ridge. Again, if we were to overlay our snow map, we can see that our model is estimating larger amounts of snow on the leeward side of this ridge, where snow also tends to persist later into the melt season, as you see from the photograph. And this is kind of consistent with the process that we would expect in this type of region, specifically wind in the photograph blowing from the right to the left, scouring that snow on that wind-facing side of a mountain ridge and actually depositing it on the leeward-facing side. And if we do, again, a bit of a dive on the internet, we noticed is that there was actually an avalanche that occurred in our simulation year just north outside of our domain. And the cause for this avalanche was cited as strong westerly winds that drifted snow onto easterly aspects, including the start zone of this avalanche path. So here, this suggests that we were actually resolving the impact of some of these more complex processes, such as wind redistribution, without the need for these complicated models that try to calculate this process and are often biased in these extreme mountainous locations. Okay, so we were really excited by the results that we saw in this project. Yet we also recognize that this was from a commercial data source. This used data from that PlanetScope constellation of satellites, which may or may not always be available to us. It's also at 3-meter spatial resolution, which is really great if we care about distribution across the meadow, but not really practical if we want to look at snow at larger regional and global expanses. So here we wanted to see whether we can, really improve our process-based models, improve on, I guess I should say, our process-based models that we commonly use to estimate snow across these larger expanses. So for instance, if I were to provide some cartoon here of a process-based model, they're typically set up to accept some rigid information from meteorological forcing, some fields of which that I've discussed we trust more than other fields. It then combines that forcing with a whole set of model physics with various complexities across our different models. And it uses that to estimate snow state variables such as snow water equivalent in time and space. But here, what we wanted to ask is, what if we could only have a model that has our most trusted information, right? What if we take that air temperature, because we trust that to a fairly high degree? What if we drop daily precipitation, but instead we give the model some long-term precipitation climatology, which we trust a lot more? And what if instead of giving, these meteorological fields, we also provide an observation, such as, in this case, snow cover evolution as observed from MODIS? You may already be anticipating this, but one way that we want to do this is see whether we can sort of leverage our new generation of artificial intelligence and machine learning approaches. And specifically today, I'm going to be talking about a model called a long short-term memory network, or LSTM. I'm not going to dive into the specifics of what that model really is, but one thing to know about this is it's a really good model to learn time series of information. And especially for seasonal snow, which disappears every summer, it has this really good way to pass pertinent information along these longer, say, seasonal timeframes, in addition to the daily information necessary to resolve the daily change in SWE from one time step to another. Here, we actually trained our model using this Western US snow reanalysis that I discussed earlier on in this talk. And one way you can think about this is we're seeing how well the LSTM could learn SWE from this reanalysis, which is a more complicated model, provided only these relatively few information sources, such as air temperature, climatology, and snow cover, and this new sort of artificial intelligence approach. So here to see how well we are doing, we first wanted to see how well is this reanalysis representing snow as observed across our landscapes. So here, what I'm showing in this plot is the annual SWE temporal coefficient of correlation for this reanalysis. What I'm showing in the plot itself is the cumulative distribution function of that statistic across more than 5,000 comparisons, where each comparison is a 330-day record of observations of SWE from a snow pillow, and the estimates of SWE from the reanalysis from a 1 kilometer grid cell overlapping that snow pillow. So there's a difference in scales here, right? We're comparing point scale versus some gridded estimate. Yet at the same time, we noticed that the reanalysis is doing really well, right? Pretty much all of the statistics were above 0.8 with an average coefficient of correlation of about 0.96. Now, if we add peak SWE bias onto this, we actually notice that the model's not doing quite as well, right? It's low bias relative to these snow pillows by about 30%. There could be a couple different reasons for this. First, I think it's worth, noting and recognizing that there could be a low bias in this product. Yet secondly, there's also a reason to believe that the snow pillows tend to actually observe a little bit more snow than their surroundings. So what I mean by this is when they go out and they deploy these sensors, they don't necessarily stuff them back into really dense forests or put them on a steep mountain slope that can't collect snow without sloughing to lower elevations. They tend to put these in locations such as, these open little mountain meadows that they can walk to from the road, right, to sort of maintain. And as a result, there's a lot of reason to believe that those locations actually collect a little bit more snow than, say, what would be represented from a 1 kilometer surrounding. So to kind of show a summary of these statistics, each of these dots that I'm showing here is a different snow pillow. The size of the dot represents the annual average coefficient of correlation, and the color represents the annual average peak SWE bias. Excuse me. All right, so if we were to actually add the LSTM onto this for comparison, as a recap, we really want this to track the exact line as represented by the Western US reanalysis, right? We want it to reproduce this product with essentially half the processing cost or maybe even less. And what we see here is that the LSTM is learning to do that, right? Despite actually not training the model in any of these grid cells where these snow pillows exist, we see that the coefficient of correlation for this LSTM relative to this reanalysis is almost identical. Again, if we add the peak SWE bias to this, we notice it's pretty good. It's not identical. And if we look at our spatial map, the reason for this might be focused in locations like Utah and Western Montana. And so we're currently doing some work to figure out why that's the case, why the model is performing worse in those locations. Despite that, I quickly want to add to this plot our process-based model, which is using the exact same temperature data that the LSTM is using. And we can notice overall that performance of our process-based model is significantly worse. And this is not only in the Western United States, where we're providing the training for this model, but we also can take a look at this, say, in the European Alps. And we're seeing consistently that our LSTM is outperforming this process-based model. And because of this, we've currently been doing a lot of work to expand this model out, let's say, across the entire Northern Hemisphere snow extents, as shown by these red boxes here. And sort of testing, given the training in this Western US region, can we actually use this model to extrapolate out to, say, Arctic snow in Alaska, or maybe, like I showed you, the Swiss Alps, or perhaps, or potentially, say, high mountain Asia and the Himalayas. So yeah, currently working on this, really excited to see where it takes us. All right, so for the last bit of my talk today, I kind of want to flip the script a little bit. So far, I've kind of been asking this question, provided the remote sensing observations that we have today, how could we actually estimate snow by combining that with our modeling tools and our local observations? But in this last section, I instead want to ask, what if we actually had the ability to put a snow focus satellite in space? How well could we actually get SWE globally, provided that sensor and the current models at our disposal today? And to do this, we performed what was called an observing system simulation experiment, or OSSI. If you're not familiar with these, in our case for snow, we needed three things as listed here. We needed an assumed true state of snow evolution. We needed a baseline model with performances representative of common models. And we needed some hypothetical satellite sensor. And I'll go into exactly what each of these are in the following slides. Okay, so we performed this study across the Western United States and portions of Canada, as shown here on the right. For the purpose of this conceptual, let's look here in the Pacific Northwest. And we started by performing what's called a nature run, which we're assuming is our true state of snow evolution. So we did a lot of work, and I specifically want to provide a call out to Melissa Werjezhin here, who's also here at ESSEC, who did a ton of the simulations for this. And we did a lot of work to ensure that we had as realistic of a simulation of snow across the landscape as possible. So for this, we used a state-of-the-art snow model. We used some pretty trusted forcing, and we did a lot of calibration and testing to ensure that what we were getting from our simulations was realistic. And here, we don't necessarily actually need this simulation to be the actual true state of snow evolution in space and time, but for this experiment, we assume that it is. And you'll see why that's useful here in a second. All right, in a second simulation, we performed what's called an open loop. You kind of think of this as a baseline model representative of common model accuracies. And specifically, we set up the simulation using a totally different land surface model and totally different forcing data set. And here we want the difference between the open loop and the nature run to be representative of what's commonly known to be snow model errors from our regional and global simulations. Then in a third step, we actually subsampled and added noise to our nature run simulation to represent what we think that we could actually see provided a snow focused satellite. And here we actually modeled this based on a NASA Earth Explorer mission proposal that was submitted last year. At a high level, this proposal proposed to look at snow, specifically snow water equivalent at 250 meter resolutions globally using this X and KU band constellation of synthetic aperture radar small satellites. Because we were proposing to use radar, We couldn't actually look at snow in periods when snow was melting and liquid water was present in that snowpack. Here, they proposed higher revisit frequencies, but to be conservative for our study, we assumed 10 to 14-day revisits and randomly distributed 20% error. So here, if we have some baseline simulation and we have these hypothetical satellites, we can actually combine the two through a simulation to estimate snow in both space and time, as shown here on the bottom. And by comparing this versus our nature run, we can ask, this is how close we can get to the true state of snow evolution if we were to only have this constellation of snow satellites. All right, to show some high-level results, what I'm showing here are simulations of December, January, and February, or Northern Hemisphere winter, mean snow water equivalent in millimeters. What I'm showing on the left, again, is our baseline simulation or open loop simulation, and on the right is our true state of snow evolution or our nature run. And here, assuming, we get better as we go from left to right, we wanted to see how well our, simulation with data assimilation was actually getting as close to this nature run as possible. And in fact, we noticed that results were really good, right? Spatially, we can see that the patterns from the nature run are really appearing in this data assimilation simulation, despite not really showing up in this open loop simulation. And to kind of prove this a little bit more, let's zoom into one domain. This is the Upper Colorado River Basin. What I want you to focus on in this plot are the different lines that show domain average snow water equivalent over time. And we can see relative to our nature run simulation, as shown by the black line, our open loop or our baseline model performance was significantly high biased in water year 2019. Yet, if we actually add data assimilation onto this from our constellation of synthetic aperture radar small satellites, we can see that it's approaching really closely. And that's why I'm showing with the blue dashed line in this plot. And what's cool is despite the fact that this constellation of satellites wouldn't actually be able to look at snow while it's melting, we noticed that an improvement to estimates of snow in this winter period had really dramatic improvements to our simulations of runoff later in this spring and snowmelt period. And to us, that really means that, our improvements in the characterization of snow across these mountainous climates and these cold climates would have a really direct impact on estimating, say, projections or forecasts of streamflow in these snow-fed basins. So, all right. So in the last little bit today, I kind of want to recap how we've gone through this, right? And sort of ask, where does this put us, right? I posed these applications at the start of this presentation. And certainly while these aren't the only 4 applications that snow has in our environment, what we really want to know is, do we have the capabilities to address these applications across these different spatial and temporal scales, provided the in situ observations, the models, and the remote sensing observations that we have today, right? And in section 1, we found that, spring snow cover can be used to search for annually representative snow accumulation patterns from a historic period, and that you can use those to connect point scale observations of snow accumulation with watershed scale estimates of snowfall volume and distribution. In the second section, we showed that, you can use drift scale observations of snow cover from this commercial imagery at, 1 to 5 day revisit frequencies, and actually use this information to estimate the drift scale and daily spring SWE distribution. And this included features like wind drifts and preferential deposition that are really, really difficult to simulate in these mountainous environments. And in this third section, we showed that, we can create a model that has the information that we most care from and that we most trust to actually simulate snow. We're talking our most trusted forcings and remote sensing observations of snow cover. And we're currently working to see just to what extent that we can sort of bump this out to estimate global snowpack. And, as we're going through this, you'll notice that we're filling out this graph little by little. And so the next logical question is, where are the gaps? Where should we focus our efforts in the coming years? And, I think one thing that's fair to point out is that, these observations from the commercial satellites are really awesome, yet they only span a few years, right? We don't have a long historical record of these observations. That said, in all the domains that we looked at, we also noticed that these, patterns emerged year after year after year. And if I'm willing to bet, I think that, this sort of information could be actually used to infer snow distribution in other years, including years before these satellite observations even became available. One thing I'd also like to mention is that, we're filling out this plot using only limited information from Landsat, MODIS, and Planet, and each of these studies use these in isolation. And there's no reason why we should be isolating these, right? Maybe now is the time in the snow community to use all the information that we have at our disposal, not just one model, but a whole set of models, not just one satellite, but a whole set of satellites, and sort of create this integrated approach that helps us estimate snow across these wide varieties of spatial and temporal scales. Despite that, if I have to leave you with one thing today, it's that maybe these synthesis approaches wouldn't be a replacement for what could be possible provided a snow-focused satellite. Right here in the Western US and Canada, we noticed massive amounts of improvements in our snow simulations provided this observations from this global snow-focused satellite. And there's reason to believe that it would be even better and easier snow climates to observe, such as the Arctic. So to me, this means that the snow community should continue to push for that sort of platform. And we're really excited to continue to think about all these approaches and combining them in this sort of trade space as we go forward. So yeah, for that, I think I will stop there. I'll throw out this slide if anyone wants to look into any of these studies. I'd like to thank everyone for their attention, and yeah, thanks so much.
Thanks, Justin. So any questions?
Oh, I'm so sorry.
Oh, you're sure.
Okay. Oh, I'm sorry. You mentioned those snow cap things that captures the snow. You mentioned they're in areas that are not on. Do you think if you move them, if they're moved to areas, would that change any of the results, or would the results be?
Yeah, it's a great question. And I don't know, the online has the question, right, from the microphone? Can't check the. Maybe I'll just briefly recap just in case.
Sure.
The question, as I understood it, was those snow pillows are often placed in locations that are less preferentially or more preferentially deeper snow. And so the question is, would it change results if those were moved?
Yeah.
And I think the answer is yes, right? I think especially if I'm thinking in the first section, you know, we're relating what was observed at these snow pillows using the relationship between these patterns, which could be partly biasing snowfall. We didn't actually notice any high or low snow bias based on that. But that being said, there have been studies that show that, you know, for instance, if watershed managers in the Western US rely only on what they're seeing from snow pillows, they're probably missing a part of the question, right? And maybe they're doing okay if they've had these relationships drawn from previous years. But they are in locations that are preferentially higher. And so a lot of people are looking right now at trying to create these transfer functions or estimates of, you know, what snow actually may look like provided this observation, which is in a biased location. And I think one thing to mention here too is that they tend to be at mid elevations. They're not necessarily putting them in lower elevations where snow sometimes exists or sometimes doesn't. Or at the highest elevations that they just can't access in harsh winter conditions. So there's a lot of representative issues with these pillows.
Okay. And I guess my follow-up then, considering what you said, would be, you mentioned that there was not so well performing or not so well performance in one area in particular that was of concern. Do you think maybe there is some kind of relationship there, or in terms of moving the snow pillows, or maybe that's not related?
Yeah, it's a wonderful question. Are you referencing this plot here? Oh, sorry, it's really slow. Yeah.
Yeah, it was just that one area that, yeah, where you mentioned that the results that you were seeing were not, yeah, and you were wondering what the problem may be. I'm considering that now that you said if you move the snow pillows, that would skew the results. So I'm wondering if maybe that has some kind of influence on the performances at different locations.
Totally. My guess in this case is that it's probably being driven by precipitation climatology. My guess is that when we use this LSTM that relies on a climatology instead of this model from the reanalysis that kind of treats every grid cell similarly, that the precipitation is actually biased low in these locations. That's my hypothesis right now. It's something we're currently looking into. But I think that issue in this case is probably less related to these snow pillows because they weren't used in the model training, just the evaluation. Yeah. Thanks.
Any other questions?
Hey.
think there's some online too, but
Holy
okay.
smokes.
So I had a bunch of questions, but one, so it would be like, so you're looking at the patterns, right? You're saying you might be able to like use those going forward because those similar. This is like maybe a dumb question. What do you think might happen, like if there's like fires or some, some of those things could change some of that? Is that anything to worry about or?
Absolutely. And it's, yeah, not a dumb question at all. This is a huge thing we know, and especially when you're talking about snow, when you're talking about fires, that influences how snow accumulates, right? The canopy intercepts snow, and beyond there, it can either slough it or sublimate it away. And we know that when fires come, that changes that process. It also changes because these burnt stands deposit soot onto the snow, which makes it melt more rapidly in the years following the fire. There's a whole host of reasons why patterns could actually change. And I think broader scale snow, when we're talking about the full Western US, fires impact a fairly low percentage, yet they are a fairly large impact. So it's a lot of reason why we should be treating those locations differently. Yeah, it's a great question. I don't know if I have the solution offhand, but yeah.
Actually, I got a question. So if you are going to launch a new satellite dedicated for snow remote sensing, what kind of instrument and payload you want to have on the satellite?
It's a great question. So we proposed, and I shouldn't say we, it was proposed to be an X and KU band synthetic aperture radar satellite, because that would, allow us to look at the snow in a variety of different ways. That being said, there was another proposal that was submitted to look at snow using P-band, and both, there would be a different retrieval process for the two, backscattering relative to phase change. But both were showing promise to potentially measure the snow. And so, yeah, it's something the community is actively still looking at. Yeah, it's a great question.
Any other questions? Maybe we can check the online questions because we
Oh,
there are so many
do I
online
have them?
attendees.
Yeah, if we can. I should stop sharing. I think I only have 3. Okay, Lisa may have missed this, but how do you use exactly use precipitation? Do you simulate annual accumulation, or do you also use event scale? I'm trying to think what section this was related to. I don't think in any of our studies we actually assimilate precipitation. In our first study that I presented, we use observations of these snow accumulation patterns from a reanalysis product, and observations of snow accumulation from snow pillows to actually explicitly calculate snowfall as a replacement for something like a meteorological product that we have from precipitation or snowfall. I'm trying to think. Yeah, I don't think otherwise any of the other studies use precipitation again. So if I'm misunderstanding your question, please let me know. I only see one question in my chat. Okay.
Oh, okay. Well, okay. So then we will conclude the talk, and let's thank the speaker again. and to the online attendees, we have next week we have a virtual seminar, and I think 2 weeks from now we have another in-person seminar given by Sarah from NASA GSFC. So stay tuned. Thanks.
The meeting then.